Hello, calculus class. Um, Today we're just going to be doing a few problems regarding your understanding of integration. And so I gave you a brief introduction to integration a few um, or a week or so ago, but let's just review again what it means to integrate something. Um, what does that integral sign represent again? So we know that the integral from a to b of f of x dx. There are three main ideas that that integral represents right now in our heads. And the first one is basically the mathematical definition. You should always remember that. That mathematical definition is based off actually our graphical understanding of that, which, if you recall, our first integral was that one guy running a marathon where he had another guy clocking his speeds at various intervals of time. And we got approximate distances to how far he ran by taking those values of the velocity that we had and multiplying them by time intervals. So we had a graphical understanding as well as, another understanding which we'll get to. But we estimated his overall or position change by adding up all of the differences in x times the velocities at each particular x value. This would be x sub 1 all the way up. I running from 1 to n. And then we took the limit as n went to infinity. So that's our mathematical definition. That's the limit of the Riemann sum, and that's where all integrals are based, if you recall. Then we did more graphical understanding, and we said, hey, this represents the net area bounded by the graph of f, the lines x equals a, x equals b, and the x-axis. That was our current geometrical understanding of that integral, and we will still hold on to that, but we're going to broaden that to many, many other quantities. And lastly, we said if we are to translate this for word problems, we know that the integral of f of x dx from a to b represents the total change in the antiderivative of f. So we know that integral of little f of x dx from a to b represents capital F, where f is the antiderivative of little f. So if we differentiated capital F, we'd get little f. So it's the antiderivative of little f. Capital F of b minus capital F of a. It's fundamental theorem. So three representations of, or three understandings we currently have of what an integral means. Now we're going to apply these, particularly the, well, number one, is cutting up. We're going to apply it to various procedures. And I have a set of problems for you guys that I'd like you to work on gradually. So the way I'm going to work this videotape is I'd like your substitute, Mr. Gilt, to pause when a problem is introduced and give you guys an opportunity to read it and set it up. And then you can check by hitting play for my solution. Okay? But let's recall the overall process of integration. The very first thing that you do in unfamiliar context is you take whatever region or idea you have and you divide it up into a lot of little pieces, okay, or subintervals, like we did for area. We chopped up the x-axis into a variety of delta x's. Well, not a variety, they were all the same for us, but it could be variety in the theory of the integral. So you divide the quantity up into a lot of little pieces, and then you approximate the quantity that you're looking for, be it length, like the arc length group showed us. Okay, you can approximate the length, or as we'll see, the volume, or as we have already done, the area, which was the function height times delta x on each, or really just one little piece. Okay, so we just focus our energies on one. An infinite number is way too hard to think about, so focus your energies on finding that quantity of interest on one piece. Okay? And then sum them up. You get a Riemann sum. Okay? And then what do? That's right. You take the limit of the sum as n approaches infinity. Okay? And you get the integral of a product. Okay? And that's the whole process of integration as applied to more of a general setting. Okay, but you can think of it in terms of our development of area. You know, divide the x-axis up into a bunch of subintervals. When we were looking for area, we took each subinterval delta x and we multiplied it by whatever function value we had at x sub I to get the area of that. Then we added up all of those areas to get an approximation. We used sum sequence in that. And then we took the limit of that sum and arrived at our integral, which was eliminated all of that error we had. So you should know this backwards and forwards. I think you already do. But let's move on into newer contexts. And as we do, just always recall that the units are going to give you a clue as to what quantities you'll need to set up. Okay? So you know that you're basically taking, when you're doing the integral, you're taking y units times the x units, okay? So just like we did in the area, you're taking the y units times the x units, all right? So keep in mind that means, you know, if you're looking for displacement, that means like velocity times time, meters per second times seconds, okay? Work, force times displacement. So this would be like, or I was thinking work is, yeah, force times displacement. So like foot-pounds, or um, the definition of joules is newtons. It's the definition of a joule. Physics people, as I'm trying to remember joules. Where's my recording here? That's right. A joule is a Newton meter. I'm sure many of you physics people were chuckling at my failure to remember that. I did have physics in college, but I can't remember those units of physics. So then, let's go back to this. Mass is density times volume. Population, same idea, population density though times area, like people per square mile times square miles. And length is the slope times a change in x. And just a side comment, frequently we will be representing a density with the Greek letter rho, R-H-O. Okay. So there's just a reminder that, you know, take a look at the units and they will often drive what calculations you'll need to make. Kind of like unit analysis basically is what it is. So again, the process for integration in a shorter form: subdivide, draw one, and then find whatever it is you need about that 1, sum up all of them, take the limit. Okay, it is the same as you'll see through all of our applications of integrals. So if you remember this 4-step process, cut it up, draw one, and find what it is you need about it, be it the volume, be it the area, be it the arc length, then add them all up and then take the limit to get the integral. Okay, so I'm going to give you a few minutes, and I'd like Mr. Gill to pause this video, reminding yourselves of how to find the area bounded by those 2 curves. And they are sideways curves. The independent variable here is y. So please pause at this time, set up your integral, just set it up for finding the area bounded between those 2 curves. So I hope that you guys all, I know I drew a little rectangle in there, but if that rectangle was not drawn in there, you should have drawn it. Okay, so make sure you always draw one, and then you say, I need to find the area of just that one. Now you know that the width of that rectangle is delta y, so all of your stuff is going to have to be in terms of y. And remember how we said to find that length of y? You take the right y value minus the left, the right x value. The right x value minus the left x value to find the overall change in x times delta y. But we have to make sure that that right x value is a function of y. Okay? So the right x is going to be y plus 2, as you can see in the red graph up here, and the left one is just y squared. Okay? Then you take n of them. There's your Riemann sum. Okay, you have the length times the width. Take the limit. Okay, I'm showing the formal development of the integral. You guys probably just skipped to the integral, which is just fine. Okay, and then you set up your final integral, being the integral from -1 to 2 of y plus 2 minus y squared dy. And as a verification, you might have used the limits that were shown here as -1 to 2, but here's a verification that they in fact are the limits. Set the 2 functions equal and solve for y. Okay? Factorable quadratic equation. Okay, next problem. Take a few minutes. Please pause this video and set that up. It's a very interesting problem. Very interesting indeed. I'm hoping you guys talked about what you know about Boston. On your note sheet, I have drawn a bunch of rings. Is that with Boston center in the very, very center of that circle? Is that really the way Boston looks? Hopefully many of you know Boston is a coastal city, so it really doesn't quite look like that. It looks more like this. Okay, so we kind of ignore everything off to the east because it's ocean. So we have the density being f of x, which is in people per square mile right here. So what we need really, if we're looking at just one, where our energies are focused just on one of these little tiny rings, is we need the area of that. Okay, now this is where it gets a little interesting. Okay, the area of one semi-ring is going to be in miles squared. We know that already, but how do we go about approximating that area? Well, most of you probably said the difference in the circles, okay, half of the difference in the areas of the circles, but really when you consider what's happening, you don't need that. This width of that semi-ring is delta r. And you know that eventually delta r is going to go to 0 because we have density as a function of x. The distance out really is probably r is better variable to use, but x is the distance outward from the city center. That's the definition. And it's going to change not based on, steps of like one. It's going to change infinitesimally. So what we need to do is express a neat way of finding that area of that semi-ring. So think about snipping it and stretching it out, because the curvature is not going to matter at all when delta r is going to 0. You're going to get this little, basically a little ring like this, little tiny, with a teensy weensy little tiny thickness of delta r. So when you stretch that out, it's going to be really, I mean, the difference between the inner radius and the outer radius is negligible. But I'm going to draw it anyway and stretch it out so that we can see it and talk about it. The width of that little stretched out now rectangle is delta r. And what is the length? I'll give you a second. Okay, well, the length, are you ready? Make sure you write this down. You know who I'm looking at. The length of that is pi r, because it's half of the circumference. Okay? So what we have to do is just express the area of that little one, that little tiny, tiny, tiny semi-ring, multiply it by the density, and we'll have the population in one ring. And there you have it. F of x times pi x times delta x. Isn't that cool? Yeah, that's a population in one little tiny, very, very thin ring. And of course, we add them all up, okay? We add them all up. I'm just showing a unit check because that's kind of important. Okay? Add them all up and arrive at our wonderful integral. Take the limit, of course, as delta x goes to 0 or n goes to infinity, and this is going to be our integral. And of course, we can factor pi right out and get pi times the integral from 0 to 5x times f of x dx. Okay? Cool problem. Very, very cool. I hope you appreciate that we can do this little area of one semi-ring as delta x times pi x. I'll go back down here so you can make sure and get that integral written down. Pause it if you need to copy this. Okay. Next problem is finding the total mass of a 3 by 5 rectangular sheet where the density at the distance x from the side of length 5 is rho of x 1 over x to the 4th plus 1 grams per square centimeter. So take a moment, see if you can work that problem, and pause this. Okay, your first step is to make sure you draw a picture always of this rectangular sheet. And I needed to. You may have been able to do this your own method, but I needed to kind of picture, as I moved along from the side of length x, or of length 5, excuse me, what like the whole mass of a strip would be. So you'll see me do it very rudimentarily, very rudimentary drawing. Sorry. So draw a picture. Here's my sheet of 3 by 5 that I drew. Okay. And I chopped it up just in 3 segments, just to make it easy. And we do have to assume that the density is constant within each strip. So I just did 3 strips to give myself a feel for what this Riemann sum would look like before I wrote the integral. All right. So if you are estimating, say, the mass for each strip, you would take the density at the first segment, and what's 1? That's actually the delta x, okay, times the height. So I'm taking the area of this strip. So this is the area of the strip times the density. And make sure the units work out, okay? Always make sure the units work out. So this is in centimeters, okay? So delta x, or the 1, delta x is going to be in centimeters, and the 5 is going to be in centimeters. So we have centimeters times centimeters times grams per centimeter squared. And I do it for all 3 strips. And I get an estimate for the for the total mass to be approximately 2.855. Now that's just, the only reason I did that was to develop a feel for the integral that I want to set up. Okay, I now have a feel. the 1 is going to be my delta x right here. That's just going to be my delta x. Okay. Um, and I'm multiplying that by 5 in each case and the density at each x. So I know immediately how to set up my integral, which looks like this. Well, I guess I put in a Riemann sum. I forgot. There's my Riemann sum. But we move quickly by letting the number go to infinity or delta x go to 0 to get my integral, of 0 to 3, 5 over 1 plus x to the 4th dx to be 5.49 grams. Okay? All right. Next problem. Water is flowing. So take a read, pause this, take a read, and see if you can set this one up, because this is a great practice problem for what we've just done a couple problems ago. Okay. So the thing that I always look at first is, what do I have and what do I need to get? I know I have the velocity of the water in inches per second, and I want inches cubed per second. So I know I'm going to need to multiply that velocity by an area traveling through this cylindrical pipe, namely a cross-sectional area. Okay? So I know I'm going to have to take that velocity times the area of one ring. And I think about the cross-section of the pipe looking something like this. Looks kind of familiar, like our Boston problem. And I want to find the area of just one little ring. Okay, because again, the velocity is dependent on, the precise distance outward from the center. So while I drew really a very wide, these rings are very wide, the function of velocity is going to be dependent on one fixed distance outward. So I know that my thickness of the rings is going to eventually go to 0. So I need to find the area of one ring, and I do the same thing that I did in the Boston problem. I'm going to remove one ring. I'm going to slice it. Okay, so I make a little bit of slice and I stretch it out, and the dimensions of that ring are delta r by 2 pi r, thus giving me the area of one ring to be 2 pi r delta r. Okay, so then I go back to my problem here, and I put that in for the area of one ring times 10 minus 1, 10 times 1 minus r squared, and that's the integral that I want. Integral from 0 to 1 of, that's my inches per second, and this would be in inches, and that's going to be in inches. So units will result in inches cubed per second. And I'm taking a cross-sectional area times the velocity of the water that flows through. And this is kind of a neat problem if you know Poisson's law and ideas regarding, like water flowing in a river. If you want to, if you want to go the fastest down a river, actually, you go to the middle of the river where the water moves fastest. Water tends to move slower outward from the center of the main flow, also because it sticks to the walls. Okay. All right, then the last problem I am going to let you guys work on, because this particular problem is very much like one that is in your homework, which your homework is to do the Chapter 8 packet problems, the circled problems, okay, in 8.1. All right. So take a look at those problems in 8.1, but start with this one. It's just a slight variation on one of them that's in there, but I would recommend that you draw a picture and do watch your units because they mix, or looking at the height from the atmosphere from 0 to 50 meters, whereas you're given the radius of the Earth in kilometers. So you have to watch your units. So draw a picture, okay, and figure out what it is you're going to need to add up in each Riemann sum. Okay, so that is all I have for today. Make sure you do those Chapter 8 packet Problems 8.1, and I will see you tomorrow.